In the beginning there was darkness, not the darkness of night, but a deeper stillness, a silence without memory, a void without edge. Out of this silence, light was born. Threads of brilliance stretched across the emptiness, weaving matter into form, galaxies into clusters, clusters into vast cosmic continents. The universe became a tapestry, delicate, ordered, alive. But this tapestry is not still. It breathes, it stretches, and now it begins to tear across billions of light years. The galaxies drift apart, their motion accelerating as though pushed by some unseen wind. What once was bound together by gravity now seems to slip its own leash, like glowing embers. Scattered from a fading fire, stars and worlds are cast adrift on an ocean that swells wider by the moment. Astronomers call it cosmic expansion, driven not by matter, nor by light, but by something stranger. An invisible pressure, a hidden energy that fills all space, yet cannot be touched. Dark energy, no one knows what it is, or why it grows stronger with time. We only know what it does. It pulls at the very fabric of reality, unraveling it thread by thread. And so a question haunts the night sky. Why does the universe refuse to remain whole? Why is it running from itself, faster and faster, as though fleeing some unseen fate? Somewhere in that mystery lies the fate of every galaxy, and every star, and perhaps every living thing that has ever opened its eyes to wonder. The universe is expanding, but where and to what end? Chapter 1. The first glimpses of a restless cosmos. For centuries, humanity looked to the heavens and believed them unchanging. The night sky appeared fixed, eternal, a perfect dome of stars, serene and motionless. To ancient eyes, the cosmos seemed as permanent as stone, a celestial clock that would tick forever, its gears neither speeding nor slowing. Even into the dawn of modern science, this vision held sway. The universe as a static stage, vast and indifferent, upon which the drama of life would unfold unchanged for eternity. Then came a revolution in thought, quiet at first, but powerful enough to shake the foundations of reality itself. In 1915, Albert Einstein unveiled the general theory of relativity, a new description of gravity not as a force, but as the curvature of space-time itself. Space and time, once separate and absolute, were now interwoven, a flexible fabric shaped by the presence of mass and energy. Yet even Einstein hesitated to follow his own equations to their unsettling conclusion. They hinted that the universe could not remain still. It must either expand or contract. But Einstein, steeped in the old belief of a static cosmos, resisted this vision of a restless universe. To preserve the illusion of eternal balance, he added an extra term to his equations, the cosmological constant, a mathematical patch to hold the universe steady, like an engineer forcing a machine to stay at rest against its natural motion. But nature does not obey human preferences. In the thin, cold air atop Mount Wilson in California, a new eye was opening on the heavens. A 100-inch telescope, the largest of its age, gathered the light of distant galaxies, pinpricks of radiance that had traveled millions of years through space. Astronomer Edwin Hubble, meticulous and patient, measured these lights and compared their spectral fingerprints. What he found would overturn centuries of certainty. In 1929, Hubble revealed that the galaxies were not fixed beacons on an eternal night. They were fleeing, all of them, in every direction. The light they emitted was stretched, reddened, as though space itself were pulling apart beneath it. The greater the distance, the faster the retreat. This was not a motion through space, like ships passing in a cosmic ocean. This was space itself swelling, carrying the galaxies with it like leaves adrift on an ever-widening river. The universe, it seemed, was alive with motion. The implications were staggering. If everything was expanding now, then long ago it must have been closer, denser, hotter. The cosmos was not eternal after all, but had a beginning, a moment when all space, time, matter, and energy were compressed into something unimaginably small. From that singular origin, it had erupted outward, setting time itself into motion. Einstein, confronted with Hubble's evidence, abandoned his cosmological constant, calling it the greatest blunder of his life. The universe did not require artificial balance. It was a restless thing, dynamic by nature, swelling outward as though following some deep, invisible command. For the first time, humanity understood that the night sky was not a monument carved in stone, but a living history written in light. A history of expansion, of change, of time unspooling in all directions. Yet this revelation raised questions even stranger than the ones it answered. What power could set all of existence into motion? What force could fling galaxies apart across the abyss? If the cosmos had a beginning, what lay before it? If it is stretching now, will it one day slow and fall back inward, or will it continue to expand forever, growing colder and emptier without end? The static universe had died, and with it died the comforting illusion of permanence. In its place stood a new, unsettling vision, a universe with a birth, a history, and perhaps a destiny. In the quiet dome of Mount Wilson Observatory, under the faint hum of motors and the turning gears of the great telescope, the old cosmos slipped away, and a restless, breathing universe took its place. Chapter 2: The Assumed Fate. Expansion slowed by gravity. The discovery of an expanding universe brought both awe and unease. If space itself was stretching, surely gravity, the most familiar of cosmic forces, would resist. Like an invisible net, it should slow the outward rush of galaxies, tugging gently at the edges of the cosmos, striving to pull it back toward itself. For decades, this vision guided cosmology. Gravity was universal, relentless, patient. It binds planets to stars, stars to galaxies, galaxies to clusters. It was natural to believe it would bind the universe as a whole, restraining its flight through the abyss. The question was not if gravity would slow the expansion, but how much. Scientists imagined two possible destinies, both governed by mass and motion. If the universe contained enough matter, stars, dust, dark, unseen mass hidden between galaxies, its own weight would eventually overcome expansion. Like a thrown stone reaching its peak and falling back to Earth, the universe would reverse course, collapsing inward in a fiery big crunch, an ending that mirrored its beginning. If the cosmos contained less matter, not quite enough to stop the expansion, then space would continue to grow, but ever more slowly, asymptotically approaching stillness. The expansion would coast to a halt, galaxies suspended in a delicate balance between outward flight and inward pull. Either way, the logic seemed sound. Gravity was the master architect, the universal lawgiver. Surely it would shape the ultimate fate of all things through the mid-20th century. Observatories on mountaintops and high desert plateaus scanned the heavens, searching for signs of this predicted slowing. Astronomers measured the redshift of distant galaxies, comparing their speeds and distances, mapping how quickly the universe expanded in its youth versus its present age. New techniques pushed these measurements deeper into the past, where the light was older and carried a more ancient story. By the 1970s and 80s, cosmologists grew increasingly confident. The universe behaved like a clock governed by gravity's steady hand. Though the precise amount of matter remained unknown, much of it invisible, perhaps in the form of mysterious dark matter, it seemed inevitable that gravity was slowing the expansion. The only debate was whether the cosmos would one day fall back inward or simply drift towards stillness. The reasoning was elegant, almost comforting. Expansion, after all, could not go on forever. Even if the universe was vast beyond comprehension, surely it was bound by the same predictable rules that govern falling apples and orbiting moons. The cosmos was immense, yes, but it was still mechanical, a grand celestial machine. Its gears wound by the initial explosion of the Big Bang, its springs slowly running down under the familiar pull of gravity. This belief shaped the great projects of observational astronomy. Teams built more powerful telescopes, launched satellites above the distorting veil of Earth's atmosphere, and refined the art of cosmic measurement. They searched for the cosmic slowdown with almost serene certainty in the deep sky. Type Ia, supernova, exploding stars that shine with a predictable brilliance, became their beacons. Because these stellar explosions always reach nearly the same intrinsic brightness, their apparent dimness reveals their distance, while the stretching of their light reveals how fast they are receding. By comparing near and far supernova, astronomers expected to chart the slowing pace of cosmic expansion with exquisite precision. The universe appeared to offer no surprises. Its fate, though distant, seemed knowable. Either a final collapse, a slow glide to stillness, or something balanced. In between, the cosmic drama would unfold in a way gravity alone could script, and humankind had only to measure and wait. Yet beneath this calm expectation, the cosmos was holding a secret, a force more subtle than gravity, more pervasive than matter, lay hidden in the darkness between the stars, unseen, unmeasured, but patiently shaping the universe's destiny. When it finally revealed itself, it would overturn not just the predictions of astronomers, but the very understanding of what the universe is. Chapter 3. The astronomers who stumbled on the impossible. By the last decade of the 20th century, the universe seemed almost predictable. Gravity would slow its expansion, of that nearly everyone was certain. The only question left was how much. Was there enough matter to one day halt the outward rush of galaxies, or would the cosmos expand forever, its growth gradually running down like a fading clock? To answer this, astronomers turned to the most reliable beacons in the universe, Type Ia supernova. These colossal stellar detonations shine with near uniform brilliance, their light so steady that they serve as cosmic yardsticks. By comparing their true brightness to their apparent glow in the night sky, astronomers could calculate their distances, and by examining how much their light was stretched, shifted toward red wavelengths by cosmic expansion, they could measure how fast the universe was growing at different points in its history. Two rival teams led this effort. In California, Saul Perlmutter and the Supernova Cosmology Project. Across the globe, Brian Schmidt and Adam Rees leading the High Z Supernova Search Team. Their competition was fierce, but their goal was shared: to measure how much gravity had slowed the universe's expansion since the Big Bang. They expected to find a cosmos decelerating under its own weight, either gradually or steeply enough to signal an eventual collapse. What they discovered instead was unthinkable. In 1998, as data from distant supernova poured in, a pattern emerged. These ancient explosions were dimmer than expected, not because they were intrinsically faint, but because they were farther away than they should have been if the universe were merely coasting or slowing. The expansion had not decelerated. It was speeding up. The universe was not obeying the script gravity had written. It was as if some hidden hand were pushing galaxies apart, faster and faster, with every passing billion years. The implications were staggering. A cosmos once thought to be winding down was, instead, racing outward as though driven by a force stronger than gravity itself, a force no one had predicted. Astronomers gave it a name, though not an explanation: dark energy. An invisible pressure pervading space, accelerating the expansion of the universe. Rewriting its future, the discovery shook cosmology to its core. The universe was not slowing toward a graceful stillness, nor poised for a future collapse. Instead, it was tearing itself apart at an ever-increasing pace. Far from being bound and mechanical, the cosmos was wild, restless, governed by something unknown, something that made up the majority of its total content, yet escaped all direct detection. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for revealing this cosmic acceleration. But prizes could not soften the deeper question: what is dark energy? A property of space itself? A quantum field lurking in the vacuum? Or something even stranger, a sign that our understanding of gravity is incomplete? The night sky, once thought eternal and calm, now looked unstable. Its very fabric was swelling at the edges, driven by a force no eye could see, no instrument could touch. The universe had become an enigma far larger than anyone had dared to imagine. And as humanity peers deeper into this mystery, one truth grows clear: the cosmos is not simply expanding. It is accelerating toward a future we do not yet understand. The answers lie in the darkness, waiting to be found. If these mysteries ignite your curiosity, let it take you deeper. Like this journey, share it and follow it to its edge. Subscribe. Press the bell icon and stay with the story as we search for what lies beyond the reach of light itself. Chapter 4: The Scientific Shockwave, the Discovery of Cosmic Acceleration, struck astronomy like a bell in the void. A single revelation whose echo rippled through every theory of the universe. No known force should behave this way. Gravity, as described by Einstein's relativity, is always attractive. Matter pulls on matter, warping space-time to draw everything together. It sculpts planets and stars, binds galaxies, builds the great cosmic web of clusters and filaments stretching across billions of light years. Nothing in this elegant framework predicted that space itself could push outward and push harder with time. Yet that is what the supernova revealed. The universe was not merely expanding, it was accelerating, as though driven by an invisible pressure swelling inside the vacuum. A silent engine humming in the dark. This realization was more than a scientific surprise. It was an existential one. If the expansion continues to speed up, distant galaxies will eventually slip beyond the limits of what can be seen. Their light, stretched endlessly, will fade into darkness, until entire cosmic structures vanish beyond our observable horizon. The night sky of the far future will grow empty, starless, a lonely island adrift in an ocean of nothingness. For decades, physicists believed gravity would slow the expansion. Now they faced a contradiction at the heart of nature. Relativity had predicted attraction, not repulsion. The cosmos itself appeared to defy its own laws. Amid the shock, a ghost returned from history. Einstein's long-discarded cosmological constant, a mathematical term he once invented to hold the universe static, then famously abandoned as a mistake, was suddenly resurrected. What if that constant was real, after all, not as a stabilizer, but as a source of cosmic repulsion? Space itself might possess energy, a uniform pressure that drives galaxies apart. This idea became known as dark energy, not because it is made of darkness, but because it remains unseen, unknowable. It is not matter. It is not radiation. It leaves no trace but its effect, an accelerating cosmos. If this strange energy is indeed the cosmological constant, its strength is astonishingly small, yet on cosmic scales, overwhelming. A single teaspoon of it would hold almost no measurable mass. But because it fills every cubic centimeter of space, its cumulative effect dominates the universe. It shapes the past, commands the present, and may define the future. The scientific community reeled. Why should empty space have energy? Why should this energy grow more important as the universe expands? If dark energy is constant, why does it have precisely the value that allows galaxies, stars, and life to exist before tearing the cosmos apart? Any higher, and the universe would have exploded too fast for matter to form. Any lower, and gravity would have crushed it long ago. These questions were more than technical puzzles. They hinted at something deeper, that the universe may not be governed by familiar forces alone, that space-time itself may hold secrets still hidden from human eyes. Cosmologists raced to measure dark energy with greater precision. Satellites like NASA's WMAP and Planck mapped the faint afterglow of the Big Bang, the cosmic microwave background, revealing that nearly 70% of all energy in the universe takes this mysterious form. Ordinary matter, the atoms of stars and planets, accounts for less than 5%. The rest is dark matter and dark energy, unseen, untouchable, and almost entirely unknown. The shock was not just that the universe was accelerating, but that humanity suddenly understood so little about what it is made of. The familiar world of stars and galaxies turned out to be only a thin film on the surface of something much vaster. Dark energy had no rival explanation, no particle detected, no field measured, no theory complete, and yet its presence could not be denied. A century after Einstein bent space and time into a single cosmic fabric, scientists now faced a fabric that pulls apart on its own, as if the universe carries within it the seeds of its own unraveling. The discovery did not close. A chapter in cosmology, it opened one. A chapter written not in certainty, but in wonder. Chapter 5. What is dark energy? The universe, it seems, is filled with something no eye can see, no instrument can touch, no experiment can capture. It is not stars, not dust, not the mysterious, invisible mass that binds galaxies together. It is something else, stranger than matter, stranger even than darkness itself. Astronomers call it dark energy. It is not a minor presence. It is the dominant component of the cosmos. Roughly 70% of everything, of all the energy that exists, is in this unknown form. The rest is divided between dark matter, which makes up about a quarter, and ordinary matter, the atoms of planets, stars, oceans, and living beings, a mere sliver of 5%. All that humanity has ever seen, touched, or measured is only a thin crust on the surface of a vast hidden world. Dark matter, at least, behaves like matter. It clumps, it gravitates. Though unseen, it follows familiar rules. Dark energy does not. It does not gather into galaxies or swirl into halos. It seems to spread uniformly through space itself, a smooth, invisible pressure woven into the very geometry of the universe. But what is it really? One possible answer lies in a strange prediction of quantum physics. In the smallest scales of nature, the vacuum is not truly empty. Quantum field theory says, even empty space seethes with energy, virtual particles flashing in and out of existence, a restless foam bubbling beneath reality. This vacuum energy could, in principle, act as a repulsive force, pushing space-time apart. The problem is that when physicists calculate how much energy the quantum vacuum should contain, the result is catastrophically wrong, off by a factor of 10, 120. No other prediction in science has ever been so wildly at odds with observation. If quantum theory were correct in its raw form, the universe would have torn itself apart moments after its birth. Yet the measured acceleration of cosmic expansion is gentle, unimaginably small by comparison. Somewhere in that vast mismatch lies a mystery deeper than any yet solved. If dark energy is vacuum energy, it is tuned with exquisite precision. Why should it be so small, yet not zero? Why should it appear just strong enough to drive cosmic acceleration now, billions of years after the Big Bang, at precisely the moment galaxies and stars, and perhaps life, have had time to form? The questions grow more unsettling with each step. What if empty space itself, the very stage upon which reality unfolds, is not passive, but active? What if the void is not neutral, but alive, with a hidden pressure that pushes reality apart, stretching space-time like an inflating balloon? This vision reshapes everything. The universe is not merely filled with stars drifting outward. Space itself is expanding, and dark energy is the breath that swells it. Every moment, more void comes into being, and with it, more of the energy that drives the cosmos apart. In this picture, the destiny of the universe grows cold and lonely. Galaxies not bound together by gravity will recede faster than light, slipping forever beyond the horizon of what can be observed. Their stars will fade from view. The great cosmic web will dissolve into isolated islands, and eventually even those will grow dark. Yet dark energy remains undefined, unmeasured except by its effect on the largest scales. It may be constant, a fixed property of space, Einstein's long-abandoned cosmological constant given new life. Or it may vary with time, a dynamic field called quintessence, changing as the universe evolves. In either case, its presence tells us something profound. Reality is not governed solely by matter and gravity. Something else is at work, and it permeates everything. Humanity has mapped the stars, traced the birth of galaxies, and measured the afterglow of creation itself. And yet, the very engine that drives the cosmos forward remains a riddle. Dark energy is not just a force, it is a question written into the structure of existence, a silent power that hints we understand almost nothing of what the universe truly is. Asterisk, Chapter 6, The Expanding Puzzle of the Accelerating Cosmos. The vast gulf of space, the galaxies drift like distant lanterns, their light softened by unimaginable distance. They move not because they wish to, but because the very fabric beneath them stretches, carrying them outward like leaves on a boundless tide. Over billions of years, this outward flow has not slowed. It has grown swifter, steadier, more relentless. The discovery of this acceleration began with dying stars, type Ia supernova, exploding in distant galaxies with predictable brilliance. Their light, stretched and dimmed by cosmic expansion, became a ruler for measuring the universe. In the late 1990s, these supernovae revealed a stunning truth. Faraway galaxies were farther than they should have been. The cosmos was not coasting gently outward, nor being reined in by gravity. It was running faster, as if driven by a hidden wind. But a single line of evidence was not enough to rewrite the story of the universe. Astronomers searched for other clues, and they found them. Etched into the oldest light of all, the cosmic microwave background. Born just 380,000 years after the Big Bang, this faint afterglow carries a frozen map of the infant universe. Satellites like NASA's WMAP and ESAS, Planck, measured its subtle ripples and patterns with exquisite precision. These measurements confirmed that the cosmos is dominated not by matter, but by something else, a smooth, invisible energy that drives space apart. Another sign came from the great scaffolding of galaxies themselves. Over billions of years, cosmic structures formed with a faint rhythm, an imprint of ancient sound waves that rippled through the hot plasma of the early universe. These ripples, called baryon acoustic oscillations, serve as cosmic markers showing how far space has stretched at different epochs. They too point to a universe that accelerates, its expansion guided by an unknown hand. Three separate windows into reality: supernova, the cosmic microwave background, and the large-scale structure of galaxies, all converged on the same astonishing conclusion. The acceleration is real. It is consistent. It is undeniable. Imagine the universe as a great web, illuminated by billions of points of light. Over time, the strands of this web stretch, the glowing clusters drift apart. In the far future, many will slip beyond the cosmic horizon, not because they move through space faster than light, but because space itself expands so swiftly that their light will never reach us. Whole galaxies will vanish from view, as though snuffed out by an invisible hand. This is no distant abstraction. The acceleration has been underway for billions of years, reshaping the universe while life emerged on tiny, fragile worlds. And if it continues without end, the cosmos will grow colder, emptier, and darker, an ocean whose shores recede forever. What drives this mysterious growth? Physicists call it dark energy, but the name is little more than a placeholder for our ignorance. It does not clump like matter. It does not shine like light. It permeates every corner of space, steady and unyielding, as if the vacuum itself holds a subtle pressure, whether it is truly constant, Einstein's resurrected cosmological term, or something dynamic, evolving with time like a changing field, remains unknown. What is certain is that dark energy dominates the universe. Roughly 70% of all cosmic energy lies in this invisible form, guiding the evolution of everything on the grandest scales. The galaxies we see are merely the glowing residue of a deeper, hidden reality. The accelerating universe is not just a puzzle of physics. It is a change in perspective, a reminder that humanity's familiar world of stars and planets is only a thin film floating atop a far stranger sea. The laws of nature, once thought stable and predictable, now seem to hold deeper secrets, written not in the language of gravity and matter alone, but in the very shape of space and time. As the lanterns of the cosmos drift farther into the night, they carry with them a message, one humanity has only begun to decipher. The universe will not slow, it will not hold still. It may swell faster and faster, endlessly, as though fleeing some unseen fate. And in that endless flight lies the ultimate riddle of existence. Chapter 7: Escalation of the Mystery. Possible fates of the universe does not merely expand, it accelerates, its very fabric pulled apart by an unseen force. In this silent flight outward, the cosmos may be writing the final chapters of its own story. But what kind of ending awaits a universe that cannot stop growing? The first vision is called the Big Freeze, also known as heat death. As space swells, galaxies drift farther apart, and their light grows faint, like dying embers scattered by a rising wind. Stars will live out their brief lives, consuming their fuel and fading to black. Over trillions of years, new stars will form more rarely, until stellar birth itself ceases. The night sky, once ablaze with constellations, will dim to near emptiness. Entropy, the measure of disorder, will rise without limit. Energy will spread so thin that no spark of life, no engine of motion, no chemistry of creation can survive. Even black holes, those monuments of gravity, will slowly evaporate through Hawking radiation, vanishing into a whisper of heat. What remains is a universe of cold darkness, where every atom drifts in endless silence. A cosmic candle whose flame burns, not in fire, but in stillness. Yet there is another, darker path. The Big Rip. This fate arises if the mysterious, dark energy that drives acceleration is not constant, but grows stronger with time. In such a universe, the expansion does not merely continue. It quickens exponentially, violently, catastrophic ally. First, galaxies are pulled from one another, then the stars within them, then solar systems, planets, and moons. At last, gravity itself fails to hold atoms together. In the final moments, space tears apart at every scale, shredding all structure, leaving nothing intact. If this is the destiny of the cosmos, then every bond that holds existence together will someday unravel. The ultimate erasure written into the fabric of space-time. Even if the Big Rip never comes, acceleration carves another haunting consequence. The cosmic horizon. Just as a ship vanishes beyond Earth's curve, galaxies too distant from us will cross an invisible boundary, one defined not by distance alone, but by the speed of expansion. Beyond this horizon, their light will never reach us. The universe will not shrink, yet it will seem to contract, because more and more of its wonders will slip beyond sight. In the deep future, only our local group of galaxies, bound tightly by gravity, will remain visible. All else will fade into a black void, leaving future astronomers adrift in darkness, unaware that other galaxies ever existed at all. The cosmic web, once luminous and infinite, will dissolve into a solitary island in an empty sea. These are not fantasies, but the consequences of mathematics and measurement drawn from supernova surveys, the cosmic microwave background, and the map of galaxies stretched across space. The acceleration is real, its implications unavoidable. Yet within these fates lies a deeper question. What is dark energy? If it is Einstein's cosmological constant, an unchanging property of space-time itself, then the Big Freeze awaits a slow dimming, a universe asymptotically approaching absolute zero. If dark energy evolves, growing ever stronger, then the Big Rip looms, a catastrophic disassembly of reality. And if it somehow decays or vanishes, cosmic expansion might slow or reverse. rewriting our predictions entirely. But the universe offers no easy answers. It carries its secret calmly, as though indifferent to how we imagine its end. The night sky looks serene, yet every point of light whispers of an unstoppable outward rush, a destiny beyond human scale. To contemplate these endings is to confront our own fragility. Civilizations rise and fall in the blink of cosmic time. Yet even stars, galaxies, and atoms themselves are impermanent in the shadow of dark energy. Whether the cosmos fades like an old photograph, tears apart in a sudden spasm, or simply drifts beyond our comprehension, all paths seem to lead to loneliness, an ultimate horizon where everything familiar is gone. Still, there is beauty in this vision. The universe, like a candle burning in a cathedral of darkness, gives its light freely, though it cannot last forever. Its brilliance lies not in its permanence, but in the fleeting moment when it shines, and in our ability to witness it, to measure it, to ask why it is so. The accelerating cosmos is not just a riddle of physics. It is a mirror reflecting the human need to seek meaning in impermanence. Just as stars ignite and die, just as galaxies form and fade, so too does knowledge itself burn brightly for a moment in time. And somewhere in that fragile flame lies the profound truth of existence, that everything changes and nothing stays. Asterisk. Chapter 8. Competing theories and speculations. The universe expands, and its expansion accelerates. This single observation, confirmed by supernova light, the cosmic microwave background and the great map of galaxies, is a revelation. Yet it raises a question as deep as any in physics. What force drives this acceleration? And what does it tell us about the ultimate nature of reality? The simplest answer is Einstein's old idea, a cosmological constant once introduced to keep the universe static, then abandoned, and now reborn as prophecy. In this view, empty space itself holds energy, a constant pressure that neither weakens nor strengthens with time. This vacuum energy would stretch the cosmos forever, leading to an endless expansion and a cold, silent death, the big freeze. If correct, the universe needs no new fields, no exotic particles, only the quiet weight of space-time itself. But nature is rarely so simple. Many physicists suspect that dark energy may be more than just a fixed number in Einstein's equations. They imagine quintessence, a dynamic field, evolving as the universe expands. Unlike a cosmological constant, quintessence can change its strength, waxing and waning with cosmic time. It could fade away in the far future, allowing gravity to slow the expansion. Or it could grow, tightening its grip on the universe, steering it toward stranger destinies. In the most extreme case, this energy becomes phantom energy, a repulsive force so powerful it not only drives galaxies apart, but accelerates them toward destruction. In such a universe, even atoms would be torn asunder. This is the road to the Big Rip, a cosmos unraveled thread by thread until no structure remains. Observations today do not confirm this scenario, but they cannot entirely rule it out. A reminder that the universe still keeps some of its cards hidden. Dark energy may have been hint at something larger than our universe itself. In the framework of inflationary cosmology, space may be an infinite mosaic, a multiverse, with different patches of space-time obeying different laws, each with its own value of vacuum energy. Some regions expand violently, others collapse. Ours is simply one bubble where conditions happen to permit galaxies, stars, and life If true, the question why is dark energy so small, yet not zero, may have no deeper answer than chance. We exist because we can, but there is an even more unsettling idea. Quantum field theory suggests that what we call empty space is not truly empty. It seethes with virtual particles and fluctuating fields. The vacuum we live in may be a false vacuum, a metastable state, not the lowest energy configuration of the universe. If a lower energy state exists, the cosmos could, in principle, tunnel into it, collapsing without warning into a new kind of space, a more stable reality. This would trigger a bubble of destruction, expanding at nearly the speed of light, rewriting the laws of physics in its wake. There would be no alarm, no signal, no escape. One moment, the familiar universe of stars and atoms would exist. The next, it would be gone, replaced by a different world, or by nothing at all. Though calculations suggest such a decay is extraordinarily unlikely within the current age of the universe, the possibility remains a chilling reminder. Even the vacuum itself is not guaranteed to last forever. Each of these theories, cosmologicals, constant, quintessence, phantom energy, multiverse, false vacuum decay, is drawn not from fantasy, but from the mathematics of modern physics, sharpened by observation. Yet they point to radically different futures, from an eternal expansion to sudden annihilation. The cosmos we see today, with its graceful sweep of galaxies and its delicate cosmic web, is only a snapshot in time. Its long-term fate is still unwritten. Behind every starry night lies this profound uncertainty. Are we drifting on a tranquil sea of constant dark energy, destined for a slow, frozen twilight? Are we sailing toward a storm of phantom forces that will rip space-time apart? Or are we adrift in a fragile bubble, one quantum fluctuation away from dissolving into something unrecognizable? The search for answers has driven some of humanity's most ambitious projects. Space telescopes such as Euclid and observatories like DESI and the Vera Rubin Observatory (LSST) are mapping billions of galaxies to trace how cosmic acceleration evolves. By measuring how dark energy changes or refuses to change, they may distinguish between a cosmological constant and a dynamic field. Their data will tighten the leash on speculation, perhaps ruling out entire classes of theories. Yet no experiment may ever tell us why the vacuum has energy at all, or whether our universe is unique. These questions reach beyond physics, into the realm of philosophy, even metaphysics. In confronting them, scientists find themselves staring into a mirror of cosmic mystery, where every discovery deepens the sense of wonder, and every answer births new questions. Dark energy is not merely an astronomical puzzle. It is a reminder of how fragile our understanding of reality truly is. In its silent, invisible push, it reshapes the destiny of all things, stars, galaxies, atoms, and life itself. Whether constant or changing, benign or catastrophic, it shows us that the universe is not static, not fixed, not safe. It is alive with forces we do not yet comprehend, and perhaps never will. The sky looks calm tonight. The constellations seem eternal. But hidden in that calm is a vast unseen tide, carrying everything outward, faster and faster. Somewhere beyond the edge of our measurements, the fate of the cosmos is being decided by energy we cannot touch, and by laws we do not yet know. Chapter 9. Tools of Cosmic Inquiry. The Darkness Between Stars. Humanity has aimed its instruments outward, straining to measure what cannot be touched. The cosmos is accelerating, but to understand why science must chase whispers in a storm. Each telescope, each detector, each particle smashed in a collider is a question thrown into the void, waiting for an answer that may never come. High above the Earth, the Hubble Space Telescope mapped the retreat of galaxies with an unblinking eye. Its deep fields became windows into time itself, revealing supernova whose dimmed light proved that cosmic expansion is not slowing down, but speeding up. What began as faint clues grew into undeniable evidence. A universe propelled by something unseen in microwave light. The cooled echo of the Big Bang missions, like WMAP and Planck, traced subtle ripples across the heavens. These frozen imprints of the infant universe told a consistent story. The cosmos is dominated not by stars or dust, but by a strange energy filling empty space, an energy that bends the geometry of the universe toward flatness and drives its relentless growth. On Earth, the Dark Energy Survey has charted hundreds of millions of galaxies, measuring how their light is lensed and warped by invisible matter. Each distortion is a clue, revealing how cosmic structures evolve under the competing pulls of gravity and expansion. The coming decade will sharpen this vision. The Euclid mission, launched by the European Space Agency, will map billions of galaxies in exquisite detail, measuring how cosmic acceleration has changed over time. The Vera Rubin Observatory, with its vast 8.4-meter mirror, will scan the entire southern sky every few nights, watching for transient events, distant supernova, and subtle patterns in cosmic structure that betray the hand of dark energy. And the James Webb Space Telescope, peering into the faint infrared glow of the earliest galaxies, seeks to probe how cosmic dawn unfolded in an accelerating universe. But telescopes are only one part of the quest. Deep beneath the Earth, in massive particle colliders, protons are smashed together at near-light speed. Here, physicists hunt for any sign that quantum fields, the very fabric of reality, carry hidden energy that could explain the expansion of the universe. The calculations predict a vacuum energy trillions of times stronger than what astronomers observe. Somewhere between theory and measurement lies an error so vast it is called the worst prediction in physics. Gravitational wave observatories, LIGO, Virgo, CAGRA, add another tool to the arsenal. By listening to ripples in space-time itself, they may someday reveal whether cosmic acceleration leaves fingerprints in the way these waves stretch and fade across the expanding universe. If dark energy behaves differently in distant epochs, its effects might echo in the cosmic symphony of merging black holes and neutron stars. Yet for all this precision, science's instruments grasp only fragments of the whole. Each mission provides a shard of cosmic truth, but never the complete picture. The universe guards its deepest secret as though behind frosted glass we can sense its presence, trace its outline, but never see its face. And so humanity builds bigger mirrors, colder detectors, and deeper theories, knowing that each discovery could redraw our map of reality or shatter it entirely. The question lingers in every photograph of a distant galaxy, in every beamline where particles collide, in every trembling laser arm of a gravitational wave detector. What is this invisible pressure that pushes the universe apart? Perhaps Euclid will see its shadow. Perhaps Vera Rubin will measure its heartbeat. Perhaps quantum experiments will glimpse a whisper of its origin. Or perhaps, even with all these tools, the answer will remain forever out of reach. A mystery written into space-time itself. The search is more than scientific. It is existential. In probing dark energy, humanity is probing the fate of everything, the stars, the galaxies, even the atoms of which life is made. These instruments are not merely machines. They are keys pressed against a lock that may or may not open, and the universe waits, silent and immense, as if daring us to try. Chapter 10. Beyond Physics. The philosophical abyss in the quiet depths of space. Beyond the reach of stars and the reach of human hands lies a truth too. Vast to measure, the universe is not merely expanding, it is accelerating. With each passing eon, galaxies slip further from one another, and the fabric of the cosmos grows thinner, colder, more silent. This is not merely a scientific observation. It is a revelation about existence itself. If dark energy continues its relentless push, the distant future holds no crowded clusters of galaxies, no blazing constellations stitched across the night. Stars will age, fade, and vanish into the long dusk. Worlds will wander through an ever-expanding void, and the last remnants of light will redshift into darkness. It is a destiny tending toward emptiness, a cosmic solitude. For humanity, the knowledge weighs heavy. To understand the universe is to confront its impermanence, and by reflection, our own. The question is no longer just, what is dark energy? It is also, what does it mean to live in a universe that will not last? Albert Einstein once sought a cosmos that was eternal and unchanging, a perfect stage where the drama of nature could unfold forever. God does not play dice, he lamented, resisting the idea of randomness in the quantum world, resisting a universe built on chance. Yet, the accelerating universe revealed by modern astronomy suggests not order, but impermanence. Stephen Hawking, with a different spirit, embraced the uncertainty, finding wonder in a cosmos whose laws allow no fixed script, only change. The clash between Einstein's yearning for permanence and Hawking's acceptance of cosmic fragility mirrors humanity's own divided heart. We search for immutable truths, even as nature whispers that nothing endures, in the laboratories and observatories of Earth. Scientists chart the sky, measure the fading glow of ancient supernova, and model the future of space-time. Their work is rigorous, precise, yet beneath the equations there is an unspoken ache. Every spectrum of light, every data point, is a reminder the universe itself is mortal. Philosophers ponder whether this impermanence drains existence of meaning, or gives it shape. If everything vanishes in the end, galaxies, stars, civilizations, does that render every effort futile? Or does it make each moment infinitely precious? The accelerating cosmos invites no easy answers. It reflects humanity's need for permanence, even in a world that offers none. Our cathedrals of science, Hubble, Planck, Euclid, the Rubin Observatory, the Large Hadron Collider, are not built solely to measure nature. They are built to reassure us that we can know nature, hold it still long enough to understand it. But the universe refuses to be pinned down. Far into the future, long after Earth has cooled and the sun has died, intelligent beings, if any still exist, will look into the sky and see nothing. The cosmic microwave background will fade. Below detectability, the nearest galaxies will vanish beyond the horizon of sight. They will live in darkness, not knowing the grandeur that once filled the universe, unaware of the forces that shaped it. This is the ultimate loneliness, a universe whose vastness leaves no witnesses to its own story. And yet, even this knowledge does not erase meaning. If anything, it sharpens it. A fleeting universe demands that life, rare and fragile, matters more, not less. In a cosmos destined to grow silent, the voices that speak now become all the more extraordinary. Einstein sought a rational cosmos, guided by elegant laws. Hawking saw beauty in its chaos and impermanence. Both perspectives frame humanity's place against an infinite backdrop, a species that questions not only how the universe works, but why it exists at all. Dark energy may be a property of the vacuum, a quantum field woven through space itself, or something stranger still, a signal that our understanding of gravity is incomplete. Yet, its deeper lesson is not only physical, but philosophical, that everything drifts apart, that permanence is an illusion, that meaning, if it exists, must be made, not found. The universe accelerates, and humanity watches, a brief candle, in an infinite wind, holding its flame against the night. The search for cosmic truth is, in the end, a search for ourselves. For in probing the fate of galaxies, we confront the fate of our own hearts, a longing for connection, for permanence, for something that will not slip away. And though the stars themselves may scatter, the act of seeking binds us a defiance against the void, a quiet declaration that even in an impermanent cosmos, there is something unyielding. The instruments of science will continue to scan the skies. The theories will sharpen, the data will grow richer. Perhaps one day, dark energy will yield its secrets, but beyond the equations lies a deeper understanding that the universe does not owe us answers, only wonder. And in that wonder, fleeting though it may be, humanity finds its meaning. Closing reflection, the thread we cannot grasp the universe does not end in a blaze. It does not shatter with a cry of violence. Instead, it unravels, quietly, imperceptibly, like a single loose thread slipping through the weave of an infinite fabric. This is not a tearing of matter, not a cataclysm of stars, but a slow, silent widening of the spaces between. The pressure is not from something, but from nothing. An invisible tension embedded in the vacuum itself. Dark energy, steady and implacable, urges the cosmos outward, faster and faster, with no friction to slow its hand. Galaxies drift apart like lanterns scattered on a boundless sea, their light redshifts fading into deeper hues until it disappears beyond the limits of sight. What was once a brilliant web of clusters and filaments becomes a sparse geometry, an architecture of loneliness. The universe is not collapsing, it is slipping from our grasp. Physicists trace this acceleration with exquisite precision, measuring the faint glow of distant supernova, mapping the ancient afterglow of the Big Bang, charting the cosmic lattice as it stretches and thins. The evidence leaves little doubt. Space itself is not passive. It swells as though driven by an unseen breath, and yet the nature of this breath remains hidden. Is dark energy a property of space-time itself, the quantum jitter of the vacuum magnified to cosmic scale? Is it the curvature of some higher dimension, a hint that gravity is not what we think it is? Or is it something stranger, a force beyond the reach of present knowledge? The truth eludes even the sharpest instruments, as if reality itself is woven from a cloth we cannot touch. Like weavers watching their own tapestry stretch away into darkness, humanity glimpses only the surface, never the loom beneath. In this quiet expansion lies a profound paradox. Creation and destruction, long held as the twin engines of cosmic evolution, are overshadowed by something subtler, a force that does neither, yet undoes both. It is not the birth of stars or their fiery deaths. not the collisions of galaxies or the swallowing of light by black holes. It is the void itself, asserting its dominion. The most powerful force in the universe may not be explosive or violent, but empty, a patient widening that erases without breaking. No sound accompanies its advance. No edge marks its boundary. It is an abyss that does not fall, but grows. Human beings have long sought meaning in permanence, but the cosmos offers only motion, an endless drifting apart. Even if tomorrow the mystery of dark energy was solved, even if its equations fit perfectly on the chalkboard of human thought, the deeper truth would remain. The universe expands whether or not we understand it. As epochs pass, fewer stars will remain visible in the night sky. Civilizations yet unborn may live beneath heavens stripped bare of galaxies, never knowing they were once surrounded by light. The cosmic story will continue, but without an audience. Perhaps this is the most haunting revelation, that the universe does not need witnesses. Its unfolding does not depend on being seen. The widening void is not a tragedy to itself, it simply is. And yet, in the face of that silence, life fragile, transient, luminous, insists on asking questions. The instruments of human curiosity reach ever farther, chasing the fading glow of ancient light. With every discovery, the thread slips a little more. The weave loosens, and still we follow. The closing reflection is not despair, but awe. For even as the cosmos drifts toward emptiness, the very act of seeking to understand it is an act of defiance. To measure the void is to say that absence does not have the final word. To name the force that drives the galaxies apart is to weave our own thread into the fabric, however briefly, however thin, in the end. The universe will continue its quiet flight, whether or not minds remain to contemplate it. But while they do, while questions still rise like sparks against the infinite dark, there is meaning not given by the cosmos, but forged within it. And as the last image fades, one thought lingers like the afterglow of a vanished star. Perhaps the greatest power in existence is not the creation of matter, nor its destruction, but the steady, unstoppable widening of the void, a force without anger, without mercy, without end. The fabric unravels, the thread slips away, and the universe drifts on, silent, eternal, unknowable.